Sorry, but, you know, that would have been really distracting the entire time. All right, so where we left off, right, this is 16 because double this, 4, passes in 4 here. 2 times 4 becomes 8. So 8 comes out of this, and it becomes 16. Of course, we can reuse this multiple times, right? Double this. 5 times 2 would be 5 times, pass in 5 over here. 2 times x, that returns out 10, right? Just like you would a function. How you can call function once with one argument, call function another time with another argument, and get out an answer. So 10 times 2 is 20, right? Now, as I was mentioning, we can return multiple arguments. So let's go with get multiples through 5. Okay, which is a terribly long name, but the function is well defined. Basically, here I'm just going to simply calculate, and you can return multiple values like this. Return x, comma, and basically you just separate by comma all the stuff you want to return. 2 times x, 3 times x, 4 times x, 5 times x, right? These are the multiples of x through 5, right? That makes sense to everybody? It's not a particularly elegant way to do it, but it's more for, again, just the purpose of teaching you how to return multiple things. So here, and since I'm returning 5 things, I can actually have this. A, comma, B, comma, C, comma, D, comma, E is equal to get multiples through 5. And let's go ahead, and these are the multiples of 5 through 5, right? So, and, well, first let's check to make sure it doesn't crash. Oop, what did I forget? The error is on line 10, which is on this line. What did I forget? Colon, right. I make the mistake all the time. The difference is because I know immediately what the mistake is because I've made that mistake a lot. The only way you're going to get better is by making mistakes a lot. It's okay to fail, okay? Metaphorically speaking, it's probably not okay to get an F. So, it's okay to be wrong, though, and to try it. So, okay. So, that works. Apparently, the syntax I put in is perfectly kosher. Well, I don't know about kosher. I don't know what the rabbinical authorities have to say about it. But now I can print them out like this. A, B, C, D, E, all separated by commas. 5, 10, 15, 20, 25, right? It's got them all. If I want to print them out separately, I could totally do that too. A, print, B, print. And then I could totally do C and D together. Or actually, I could do C and E together. It doesn't really matter, right? Because they're all separate variables right now. D, print, E, right? They're all separate variables, so it doesn't matter how I print them, right? 5, 10, 15, 20, 5, 10, 15, 20, 25, and then here I showed you could print out C and D, or C and E together, right? You can just separate stuff by commas like that, and it'll print it out. By default, right, as you may have learned, by default, when you print stuff out using the print function, and there are different things that are separated by commas, it will just separate them by spaces but when it prints it out. We can actually add an additional argument over here called sep, and that stands for the separator. If I put in, and that basically says how are these things that are separated by commas going to be separated. If I put in an empty string, it just glues them all together, right? That's how, because they're separated by nothing now, right? See how they were separated by nothing? And so they're separated by nothing. And then I can do /t to separate them by tabs, right? Because now they're separated by tabs. That's pretty useful. And hopefully you've learned, you went and found out about that. But it's a pretty cool, so that's something we can do. But like I said, so it's possible to return multiple things in Python. In other programming languages, like Java, the computer just gives up and cries for some reason. I don't know why. And it's a feature in Python. When I don't have it, I really miss it. Because the other programming languages do it is by kludging. Is that you personally have to make a kludge. You have to. If you want to return two things, you better make a list of two things or an array of two things and return that and then unpack what you want to return. Which actually is how Python does it. It just does it automatically for you. Let's go ahead and now, I'm going to call this again, but this time I'm just going to go and do 1. All the answers is equal to get multiples through 5, right? I need 5 things. I'm just giving it 1. That shouldn't work, right? By the way, in this class, the vast majority of the time, you're only ever going to return 1 value. I'm just trying to show this off so that you know, because again, this might be the only programming class you take, because, you know, some of you are seniors, some of you are just taking this because you want a bit of programming. So it didn't crash, right? Here's all the values from the first attempt we did, but from all the answers, it printed them all together in what's called a tuple, which is a really weird word. I don't go into tuples too much except to say that they're like lists, but they're immutable lists. You can't change a tuple. But it's useful if you need to group stuff together. So when you return multiple things, Python just packages it up into a tuple, and if it sees that you have multiple answers, if you have multiple variables over here, it's automatically going to unpack that tuple for you. In general, best way is just not to think about it. Instead, if you've got multiple variables you want to return, just have 1 variable for each thing you want. But in general, we're only going to be returning 1 thing. Now, I mentioned before, as I mentioned while the screen was out, we can only return we return basically ends a function. Once we hit a return, nothing else is going to happen, right? Print this is before the return. So this is going to be one basic example, but then I'm going to show another example, right? This is after the return. Other programming language I think would yell at me, but Python says I don't know, I'm going to assume you know what you're doing. Double this, 15. So run it. This is before the return. Notice that this is after the return, never got printed out, right? Because I pass in 15. This is before the return. We print that out. Return 2 times 15, so we'll return 30. So print. So often, a lot of times you'll do this, print, then the function call. So we got 30 back. Like I said, basically it says you returned, I'm giving you your answer, you don't need anything else, right? So, and that's because there are pretty much no cases where you actually need to, basically, when you call a function, you want an answer. Return says, I've got that answer, here it is. So there's no need to continue. Okay? And it doesn't matter where it is. It doesn't matter where it is in the function. So let's see. So let's go ahead, and that's kind of important here when we talk about doing something like an accumulator, because I'm going to show you one of the most common errors I see, and it drives me insane because I really want to make sure you understand that return means we stop. You got to return at the end. So let's talk about the accumulation pattern, as we call it. An accumulation pattern is when we use a for loop and within a function to basically add up a bunch of stuff. And we kind of saw that with strings, but here we're going to just do something basic. Def summation n. And let's go ahead and describe what summation does in the comments. Comments, unlike YouTube comments, should be meaningful over here, so we should describe what it does. So returns the sum of the numbers 1 plus 2 plus 3 dot 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 dot. I said dot 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 plus n minus 1 plus n, which if you're taking Calc 2, this is probably something that's giving you flashbacks, right? And we're not going to do it by returning. And if you happen to know the formula, we're not going to return it by returning n times n minus 1 over 2. That'd be cheating. Instead, we're going to actually add it up. So we're going to return the sum of the numbers 1 through n. So that's 1 going up to and including n. Let's define what we're going to do if, so let's see, if n is 0 or, sorry, if n is less than 1, we're just going to return 0. So the way an accumulator works is typically we use it to add stuff. We'll say something along the lines of sum, except sum is a protected word, so I'm going to use total. It's not protected. It's just a used word in Python. Total is equal to 0. And what we do is that we want to add up all the numbers individually. And let's see. Properties of addition, right? There's all those properties of addition. I'm not a mathematician. I just play one on TV. Right? There's the commutative, associative, and identity properties of addition, right? Ooh, let's go ahead and hit these, right? Come on. Commutative. So you've got commutative, you can add in any order, and you can group any number in any combination. So we're going to be using basically the associative property, which is that you can add 1 plus 2 together, and then we can add 3 to 1 plus 2, and then we can add 4 to 1 plus 2 plus 3, right? It all adds up. So in other words, we can add one number at a time to our sum and get the total sum, right? That's just a high-level way of kind of describing something that should be fairly intuitive, but sometimes you need to drive that home in terms of mathematics. So for num in range, so we're going to start at 1, right? We're going to go start at 1 and go up to and include n, right? So we're going to go up to n. And we're going up by 1, so we could put 1 here. Actually, we're going up to n, so we want to go up through n, so we want n plus 1, right? So we can include n. And right over here, right, it says 1. We could go up by 1s, but we'll go ahead and leave that out because we're going to be going up by 1s by default, right? So this is 1 to n. So the way an accumulation pattern works is very simple. Total is equal to total plus number. Basically, we take our first number, add it to our total, then we take our second number, add it to the total, take our third number, add it to the total. So if n was 3, we'd be adding 1, then we'd add 2 to get a total of 3, then we'd be adding 3 to get a total of 6. I know that seems a bit tedious and I might be treating you like, you're idiots or something. I'm not. I'm just kind of explaining it this way because when we start dealing with, decimal places and stuff we can't do in our head, it gets a bit trickier. But basically, we're just adding one number at a time over here. And then at the end, once we're done and we get our total number, we'll return the total. Okay? Now, here's the most common mistake I see with accumulation patterns. That is the most common mistake I see. because what this means is that we get total is equal to 0. So we start there, we take our first number, 1, add it to the total, and then we immediately return our total. So we return 1 no matter what happens, because the return is inside the loop, right? And remember, when we hit a return, we stop, right? Does that make sense to everybody? So we go through the for loop and then we return, right? Okay, so let's go ahead and print summation of 5. So summation of 5 should be 15, right? 1 plus 2, and we can print out, if you're uncomfortable, we can just always print out our steps. Print out num, total, and then we're going to separate it by, and then I like this trick. I really like separating it by commas. It's just, we start with doing concat. We don't start this way because it's just so much easier to do it the other way. Or rather, it's less to think about to do it the other way. So first step, we take 1, and num is 1, then 1 is our total. Then num is 2, 3 is our total, 1 plus 2. Then we add 3 for 1 plus 2 plus 3, which gives us 6. Then we have 4, which gives us 10, 5, which gives us 15. Make sense to everybody so far? Okay. Again, most of the math we're going to do is very easy. But now the math we're going to do is not. So let's talk about pi. Okay? Pi is an irrational number. What does that mean? Yes.
Can't be expressed as 2 integers over
Right.
A divided by 1 B.
Right. We can't express it as 2 integers over each other. It means that basically that there's no fraction we can create that properly expresses it. It also means that basically that this over here, when they say dot, dot, dot over here, it means it goes on forever. Also, there's no pattern to it. In fact, one of the most interesting things about pi is because it goes on forever and basically that we can't do it. It means that any numerical sequence ever created is stored in pi, which means that any rendering of any data is stored somewhere in pi. Just takes a while to figure out. And in fact, part of it is all being, and so we never really use the value pi exactly when we're actually expressing actual numbers, because that's a lot of decimal places, right? You probably remember something like sig figs from chemistry. Essentially, yes, we just simply go and say, that's good enough. Typically, right, we first learned that it's 3.14 because that's good enough for a lot of uses. And then if you're doing other stuff, you might go 3.14159, right? I don't have pi memorized. There's 2 types. You can remember, basically you can remember either that pi is 3.14159 because that's good enough for basically all the cases. Or you're the type of person who memorizes the first 100 digits of pi because that's how many digits are on the page of the book you're reading. So anyway, so attempts to memorize the value of pi have led to records of memorizing 70,000 digits. That's actually pretty impressive. Yeah, well, competitive memorization is a thing. Those people are weird, just like all people are weird, because all people have something that they're really obsessed about. For me, it's RPG. It's tabletop RPGs. For some reason, I can just remember any tabletop RPG kind of thing. It's very weird. I just saw the magic word. Ancient civilizations have required fairly accurate computed values for pi for practical reasons, including the Egyptians and Babylonians, e.g., basically just because they were old just because they were thousands of years ago didn't mean they were dumb. And they needed pi because you can't build stuff without doing some calculations. So around 250 BC, the Greek mathematician Archimedes created an algorithm. Ooh, there's that word, algorithm, for calculating it. Chinese mathematics did 7 digits. Indian mathematics did 5-digit approximations using geometry again. So they eventually we got into something called the Leibniz formula. But let's go ahead and see basically how we did the pi, right? Because this gets into what we were doing with turtles. Pi can be estimated by computing the perimeters of circumscribed and inscribed polygons. What that's saying is that basically, right, when we were drawing turtles on the screen, remember, or when we did the draw shape, as we drew more and more shapes, it began to resemble a circle, right? And basically the idea here is at some point, as we add up, we'll be able to get pi, because pi is the ratio of the circumference to the radius, right? That's the ratio from the circumference to the radius. So he computed it by drawing a regular hexagon inside and outside and successively doubling the number of sides until he reached a 96-sided regular polygon. So that was one way he did it. So the other way, though, is this of doing it was this discovery of a very interesting formula called the Leibniz formula. See, list of things named after Gottfried Leibniz. Okay? It's also called the Madhava Leibniz because, you know, it's rarely one person somewhere who discovers it. It's generally the person who becomes well known for discovering something. But it's this really interesting formula we've got over here, which is 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9, ... And basically we're saying the more terms you add up, the closer you're going to get to pi over 4. Okay. For reference, what is pi over 4? Right? Pi over 4, well, Python, import math. Math.pi is, that's what we got. So math.pi divided by 4. So it's about 0.785. Let's call it 0.785, right? So as we can see, adding one term, 1's pretty far from 0.785, minus 1/3, that gives us to 0.66, right? Adding a fifth, that's 0.2, so 0.83, so that's closer than both those. So we just keep adding and subtracting. It's a very weird quirk, right? We find that it works out. Why? Because there's this, here's why, right? That makes sense to everybody? Sure makes sense to me? No, it doesn't make sense to me at all. I could probably work through it, right? But who's got time for that? So, you know, so there's a proof for it. And basically it's just basic, and it uses calculus. So that's why it took a while for it to come up, because calculus took a while for it to come up. Oh, and it was first, yeah, so Leibniz discovered in the where was he? He was, what century was he? 16th, 17th century, so 1600s, yeah. But Madhava, who was an Indian mathematician and astronomer, he figured it out, you know, a couple hundred years before that, so good on him. But, of course, you know, he wasn't European, so he doesn't get credit. It's very cruel. So, what we can do is that we can use this kind of, we can use this formula, the Leibniz formula, to approximate pi over 4, right? And then what we can do is that we can get our answer, multiply it by 4, because, right, pi over 4 times 4 would give us pi. So here I'm going to pass in an n. And here n does not mean the, n is not like, here n is the number of terms that I want to add. So if I say, give it 3, I'm going to say 1 minus 1/3 plus 1/5, right? Because that's 3 terms total. 1/7, if I do 4, it's going to go 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9. So this is something that's going to have to alternate as well. So right now, let's just work on, so how do we do this? So the answer is that we break this up into parts. I'll figure out the alternating in a bit, right? And right now it's 1, so let's just do 1 plus 1/3 plus 1/5 plus 1/7 plus 1/9, because that's flipping. We can deal with flipping, as we go. Also, note that the series is 1 over 1/3 plus 1/5. That's a bit hard for a for loop to do. But what's not hard is 1, 3, 5, 7, 9. So let's start with 1, 3, 7, 9, right? Everybody make sense? Because the 1 doesn't change up top, but this part does. So, right, build it up small part by small part if it looks overwhelming. So let's start but we're going to create our pattern even if our pattern's going to be wrong. Total is equal to 0. We're going to do this n terms, so for blank in range. Well, actually, let's do for num in range. Here I'm going to go 1 up to and including n. Let's see. So we have, because we have 1 minus 1/3, so here, let's see. Let's just do it n times. Let's just do it n times right now. I'm not going to get ahead of myself. We're not going to do anything. We're going to go ahead and just print num and return total, which is going to be 0 for a while. And because, again, I want to get these number sequences working first before we start adding things up. So print Leibniz, which I probably misspelled, but, I'm sure he can, I'm sure if he's upset, he'll file a complaint. 1, 0, 1, 2, 3, 4. That 0 there is because the total is 0. So we've got our things over there. So now we want 1, 3, 5, 7, 9. So if I do num plus 1, I'm going to get 1 through 5. But now it needs to go up by 2 each time. Now I could modify the range up here, but I don't want to mess with that. I just want n to be the number of times that it goes. So I could say num plus 1. Let's actually work this out and make some variables. Because this is the denominator I'm trying to figure out. Denominator is equal to num plus 1 time. Actually, it should be num plus 1 times, right. It is 2 times the number plus 1. Just took a little bit of mathematics to figure it out. But if we start out so this should be 0, right? And then n will be 1, and then n will be 2. And so if we add 1 to that, that's going to get 1, 2, 3. But we want it to be spread out more. So if I multiply by 2, we'll start out with 2. Then 1 times 2 plus 1 is 3. 2 times 2 plus 1 is 5. So let's print the denominator out. 1, 3, 5, 7, 9. Right? That was the hard. Now since I put it in a variable, that's actually going to be pretty easy, because to print the numerator and the denominator, print 1 denominator separated by a slash. Right? Let's just print them out right now. 1 over 1, 1 over 3, 1 over 5, 1 over 6. Right? Those are the numbers we want. Everybody see that I'm just basically denominator is the only thing that changes, and all I'm doing is printing out 1 over that. Right? It's easier than calculating what is 0.33, what is 0.2, right, and all that stuff. Now, if I do this, so now what I need to do is also make sure that we're doing is that it's going to be negative. So every other one needs to be negative. So let's go ahead and do, let's see. So every other one needs to be negative. And I know how to solve that. I'm just trying to figure out the easiest way to explain it to you. There's a couple ways we can do that. We can multiply by -1. We can, I mean, the answer does involve multiplying by -1. It's just a matter of, do we want to do it with a for loop? Yeah. So let's go ahead and create something called the numerator is equal to 1. Okay? We'll assume it's equal to 1. But if, honestly, rather than trying to do math, so there's a couple ways. I'm going to present how to do this a couple ways. First is the easy way, the really easy, let's use computer science to solve my problems rather than trying to use math or figuring out numbers to solve my issues. Negative is equal to false, right? Because it's going to alternate. So what we do is we say, so let's go ahead and do the numerator is equal to 1. If negative is equal to, if negative is true, in other words, if it's this time to be negative, we'll just simply say numerator is equal to -1 instead, right? So we'll set up the numerator to be equal to 1, and if it's time for it to be negative, we'll say the numerator is -1 instead. And then what we're going to do is say if numerator, after we do everything, we're going to say if numerator is equal to, I'm going to condense this down into something much shorter. If numerator is, if not numerator is equal to, negative is equal to true. If negative is, if we just did a negative number, then next time we want to do a positive number, so we'll say negative is equal to false. And else negative is equal to true because we just did a positive number, so it's now time to do a negative number. Okay. Now we can just simply shorten this up we can shorten this up considerably. If negative, we can just simply say if negative, right? Rather than saying if negative is equal to true, this is an expression. If it evaluates the true, it's going to be true. If it evaluates the false, it's going to be false. So, and then over here, similarly, if negative, make negative false. But all we're doing is flipping it. And so we've got this nice, clever line. So this is perfectly fine. All I'm doing is shortening this, by the way. But what I can do to make it a bit shorter is I can say, hey, negative is equal to not negative. What does that do? Well, if it's true, if negative is true, it takes it, nots it, which turns it to false, and stores false in it. If it's false, it takes the false, nots it, which makes it true, and stores it in negative. So this flips it, essentially. Make sense to everybody? This is essentially multiplying by -1. And so what we can do is now say numerator over here. And let's see what happens. 1, -1/3, 1/5, -1/7, 1 over 9. There's another way we can do alternating, by the way. So I'm just going to copy this bit because that's cool, and I don't want us to completely lose it because it's really important. But this is the other way that we typically do it. Because let me tell you, we do something on the exam that basically on the next exam, you will have a question which will require you to do some alternating, right? Like add something, then subtract, add and subtract. And you have multiple tools at your disposal to do that. The other thing to recognize is that when n is even, we're doing a positive number. When n is odd, we're doing a negative number. Or num is odd, we're doing a negative number. So we can just simply say, another way we can do this is if num, and one cool thing about this is that because of the way Python is dumb, we can actually use it to our advantage, and we don't have to make variables outside of if statements like you do in other languages, like I did over here. So if num mod 2 equals 0, if we're on an even step, right? Step 0, step 1, step 2, step 3. So even steps we add, starting at 0. Odd steps we subtract. So if numerator is equal to 1, else numerator equals -1. Also completely valid way of doing this. So we've got our numbers. Now that we've got our numbers, we can go ahead and, since we've got our numerator and our denominator and our sign all worked out, we can now add it into the accumulation. Total is equal to total plus the numerator in parentheses over the denominator, right? And this does, very usefully for us, division into floats. So this gives us 0.83. And again, we're trying to calculate, and this gives us pi over 4, right? So if we want pi, we'll go ahead and calculate, we can just return total times 4 to give us pi, or what it says pi will be. So 0.339, which isn't that close to pi. So let's go ahead and increase this up, like to 15, and see if that gets us closer. So that went up from 3.3 to 3.2. Let's go ahead and do 100 steps of this. 31315. Let's go up to 1,000. 3.14059. So close, right? 3.14159. 26. I even got the. That's hilarious. All right, 10,000. Now, incidentally, every time I'm increasing it by a factor of 10, this takes 10. It should ostensibly take 10 times longer on my computer. But your modern day computers can do addition operations so fast, it's kind of obscene. It would give somebody, if we were to teleport somebody who was working on like the Mars Apollo missions to modern day and showed them what we could do with our computers, they'd probably have like suffer an aneurysm or something from, right? Notice that there was a small, so now that I'm doing 1,000,000 calculations, by the way, notice that basically that took us, there was a little bit of a delay there. It goes boop, boop, right? A little bit of a delay. Now if we add it to 10 million operations, that should take 10 times as long. And in fact, it does take a bit longer. So I'm going to pause it there, but let's see. With 10 million operations, we get 3.14159.255, which gives us 3.14159.2. So that was all the way up, correct up until here. And then it was 553, and the answer is 653 over here. It's very interesting how those last bits are, how the last couple decimal points are really getting pretty close to correct. It's really interesting. Right? Okay. So next is, So now, as you can see, this actually takes a while for it to calculate, and you know, let's see, mathematical constant pi. I'm not sure how many digits we've been able to figure out so far. Oh, here's an interesting one. We can approximate it like this. 3, 7, 15, 1, 2, 20 in the world. Things that somebody comes up with. Oh yeah, Monte Carlo methods. We'll learn about the Monte Carlo method as well. It's not as scary as it sounds, and it actually does have a bit to do with gambling. But there's other series, right? This doesn't, it converges very slowly. Like after 500,000 terms, you only get 5 correct decimal digits, right? It takes a while for it to get close. There's also 2 over pi is equal to root 2 over 2 times root 2. Wow, okay, that's crazy. So there's a number of these. So while we're talking about mathematical sequences, I'm going to go ahead and talk about, and we'll get into Monte Carlo and approximating pi with a bit more detail later. In fact, part of my master's project was involved doing weird approximations of pi. But I want to talk about this. Let's learn and let's figure out how to do this. So the Collatz conjecture is one of the unsolved problems in all of mathematics. It's wonderful. By the way, there's a standing $500 prize for solving it because it's really unimportant. But at the same time, mathematics is just not built for solving this one. So it's very, very simple. Or as I'll let XKCD explain it, XKCD Collatz conjecture. The Collatz conjecture states that if you pick a number, and if it's even, divide by 2, and if it's odd, multiply by 3, and add 1, and you repeat the procedure long enough, eventually your friends will stop calling to see if you want to hang out. So what the Collatz conjecture says is basically that the conjecture is that you've got 2 rules. We pick a number, and then you've got 2 rules. If it's an even number, divide by 2. If it's an odd number, multiply by 3 and add 1 to it, right? And continue, right? So say if we start with 5, that's an odd number, so we multiply by 3 and add 1, so that gets us 5 times 3 is 15, add 1 gets 16. 16 is an even number, so divide by 2. 8 is an even number, divide by 2. 4, divide by 2, we get to 2. Divide by 2, we get to 1. The Collatz conjecture says that basically pick any number you pick, any integer you pick, you get to 1 eventually. And once you hit 1, by the way, notice that that's an infinite loop. That gets you 1 times 2, that gets you to, let's see. So 1 times, that gets you, multiplying 1 by 3 gets you to 4. Yeah, well, 3 plus 1 gets you to 4. Divide by 2, divide by 2. Then get back to 4, divide by 2, divide by 2. So anyway, mathematically formulated. Yep. And if you mathematically formulate it like this, even, divide by 2, odd, triplet, add 1. So here's the thing. It's a conjecture. We haven't proved it yet. If you're a budding mathematician, I highly suggest wasting a night trying to figure it out. But nobody's been able to come up with a proof. Now, supporting arguments is that experimental evidence, we have checked all values. We've checked all starting values from 87 times, from 1 to 87 times 2 to the 60th. So we've checked from all the numbers from 1 to, let's go ahead and use Python to figure that out. 87 times 2 to the 60th. And I love Python because it will give me, so we've started at this number and seen how far we could get. It's a pretty big number. All the values so far fit the collapse conjecture. But it's not proof, of course, because unless we find a counterexample. And sometimes that with these other cases, sometimes counterexamples only work when you get a very large number. So what's interesting, so what we want to do is that one of the things I like to do is eventually we'll build up to a program that basically tries to figure this out. But I want to figure out what the length of a collapse sequence is. In other words, what oh, I'm sorry. In other words, basically, if I pick a number, how long does it take to get to 1? So in other words, with 5, that was 5 to 16, 16 to 8, 8 to 4, 4 to 2, 2 to 1. 5 took 5 steps to get to 1. What I would like to do is, given a number, tell me how many number of steps it took me. Now, unfortunately, this requires us adding one more tool to our trade, the while loop. So I'm going to start us off by learning the while loop, and then when we get back on Tuesday, I'll teach more about that. We'll use the while loop to start solving these problems. Because up until this point, we've been doing what's called definite loops, right? I've explained this before. Definite loops, for loops. We know how long it's going to run. But indefinite loops, we don't know how long it's going to run. Let's go ahead and give an example. So let's go ahead, new teaching, ITP. It's classroom. ITP 2020. Okay. Now, this is like a classic case of what we want to use a while loop for. Okay. So let's go ahead. I'm not even going to bother writing a function. Let's go ahead and say text is equal to input, enter a large word, right? Text. Now, enter a large word, right? Here we'd like them to enter a large word. We'd like to enter we'd like them to enter some text that was reasonably large. But we need a way of kind of enforcing that. So we could say something along the lines of if text if length of text is greater than 10, is less than, let's go with less than 8. So 8 or larger is large. Print that's small. And then we could do something about like this. Please enter a large word. And then print you entered, and then text. Right? So let's see how this works. So I just enter a large word. Foobar. That's small. Enter a large word. Spam. You entered spam. It's not a large word, but I entered it anyway because an if statement only activates once. Make sense so far? So if I replace this if with a while, a while statement is like an if statement, but it will run multiple times. It will keep running so long as this condition is true. Please enter a large word. Bollocks. You entered bollocks. I don't know how to spell serendipitous, but if it was, But if I did, I would enter it. Amazing is small. Amazingly, you entered amazingly. Let's go ahead and enter, put a colon here, colon here. Let's go with enter a large, I think I messed something up there, so run again. Cryptomencia. Which you think, what in the world? Cryptomencia? Cryptomencia, which I failed to spell correctly, is an implicit memory phenomenon in which people mistakenly believe that a current thought or idea is their own creation, when in fact it is not. For instance, when you hear if you're a musician and you think you come up with an original piece of music, but it's not in fact an original piece of music and you just heard it on the radio a year ago. It is basically it's a very interesting word, very obscure word, but it's a fun one. Okay, so notice that basically so now let's just try to annoy the computer. A, B, C, D, E. It's going to keep doing this loop. It's going to keep running this, right? So long as the length of my text is less than 8. Okay, entered something greater than 8, so it prints out. That's what a while loop is. So long as this condition is true, it'll print it out. Now notice that basically I had to have an input statement twice. What I can do is just there are ways around that, but what I can do, like for instance, what I could do is something like this, right? So text is equal to an empty string. While the text is less than 8 longs, enter a large word. Foo, bar, baz, right? So that is how one way a while loop can work. While loops, you don't use them too often except when you just don't know when something will end, when you've got a specific condition for things to run. So, like for instance, with our Collatz conjecture, well, for our Collatz conjecture, we want to run while our answer is, while we're not at 1. So, for instance, let's see so let's actually go to your textbook for a second, Runestone, and I will give you be grading it and giving a preliminary score on it this weekend. And okay. That is frustrating that it is so slow sometimes. Okay. Transforming sequences, conditionals. Right? Don't really talk about while too much. Yeah, the while statement doesn't really come up until chapter 14, but it's useful, but it's a fairly simple thing to know. It's a very easy thing. Is the condition true? If so, do the body. Otherwise, run it again and again. Now, what's interesting is that no language needs both a for loop and a while loop, because any while loop can be transformed into a for loop. Although but the way Python has it structured, it does need both, because your for loop is a for each loop. So, but we can use a while loop almost anywhere that we need a for loop, just by being really clever about it. All right. So let's see. I think this is a good enough stopping point for right now. So on Tuesday, we will get back to you. We will get back to doing the class conjecture, and then we're going to start looking at file reading.